So in my last lecture, I started to talk about the question as to what happens when you take a composition of the Euclidean transformations. And of course, since we are dealing with concrete examples, not the abstract theory, for instance, what happens if you put two reflections, one after the other? And I answered the question partially, and in fact, I dealt with a special case, which was the following: that if you have two reflections on, let's say, okay, so the question was, if you have got a reflection in some line K, in a line K, and that is followed by a reflection in yet another line L. So what's the result? So there are two cases to be considered. The first case was, let's say, case one. Case one, it's what happens when the lines K and L are parallel. When K and L are parallel, then you can actually find a vector which is perpendicular to them both, and so that, okay, so let's call that vector U. So that in fact the second one is obtained from the first by means of translation along that vector, by that vector. Okay? So once you have got this, then the rest is easy, because a very simple argument shows that if you've got a point, then you reflect it in the first line, which we called K, to obtain the point x prime, let's say, and then you reflect it again in this straight line L to obtain the final object. So x goes into y. Well, you can readily find that the vector xy is in fact twice the vector u, so that if K and L are parallel lines and L is obtained from K by means of a translation by a vector u perpendicular to both lines, then the result of two such reflections is in fact translation by twice this vector. Okay, the vector that actually puts K on top of L. Okay, so this was what we did with the case number one. Okay, so the case where the lines are parallel. Okay, now let me continue. So let's ask the question, what happens if not? So, well, case two. Well, in that case, the two lines intersect in a point. Intersect in some point P, let's say, and they make an angle. So there is an angle between them. Let's call that angle. Let me call that angle theta. So here's the picture. Okay, so you've got one line like this, and the other line. Okay, so that's K, that's L, and they intersect in the point. They intersect in the point, which I like to call P, and the angle between them is theta. Now, okay, let me point out once again. We talked about this. People treat this as a rather obscure remark on my part, yet it's a very important thing. This theta, when you are measuring angles between lines, of course, well, you will, okay, so the angle between K and L is what happens to K, how much K is rotated if you want to rotate it about the point P so as to make it coincide with L. And that's some number theta. Yet that number theta, Okay, so if you add pi to that number, then you will again, okay, so that's theta, which makes k coincide with L. Well, add to it a pi or any multiple of pi, it will do the same thing. So this thing is angle between lines, I pointed out. So this is a quantity which is measured modulo, not 2 pi, but pi. So this is an element of the additive group of additive quotient group R by pi times Z. So this quantity is measured modulo not 2 pi, but modulo pi. Okay, so that's one thing which I would like to make a remark, which I would like to note immediately. Okay, so this is theta and it's modulo pi. Now, if I start with a point, let's say here, and then so let's say x, and if I take its reflection in K to obtain the point x prime, and then let x prime be reflected in L to obtain its final position y. Okay, so what has happened is is that, okay, so let me join px, and notice that the length of px is the same as px prime. Okay, and the length of py, they're all the same. They're all the same. So what has happened is, in fact, px has been rotated to reach y. X has been rotated about p to reach y. And the angle of rotation can be easily seen to be twice theta, because you see this angle 1 and 1, they are the same. This angle 2 and 2 are the same. 1 plus 2 is theta, so the whole angle is in fact twice theta. So this is actually a rotation. So the resultant of taking two reflections is in fact rotation. Okay, so you take reflection in K and then reflection in L. The result is a rotation about the point P, angle 2 theta, where, okay, so let's repeat, where K and L, okay, so K, lowercase L, they intersect in P, and the angle between them, the angle between K and L is theta, and theta is measured modulo pi, okay, that being angle between two lines, undirected lines. And of course, this is 2 theta, this is of course measured 2 pi. So this is modulo 2 pi. So that's excellent, there it is. So now, okay, so in a sense, if you wish, I mean, if you are that kind of person, if you are inclined to have this semi-metaphysical attitude of thinking that a point, if you let it move towards infinite, if this P is very far away, you will see X and Y as parallel lines. You will see K and L as parallel lines. So in a sense, çocuklar, just as in this example, you can understand a translation as if it were a rotation about a point at infinity, which is just a fantastic thing. You don't need to think about that, okay, for the moment. And then another point which I would like to make is the following. In fact, okay, not only two reflections in intersecting lines, reflections in intersecting line add up to give you a rotation. Not only that, but you can also conversely, now this is rather important, and I shall use it in fact, conversely, any rotation can be decomposed as the as the product, as the composition, as the concatenation. Okay, here's a new word. Of two reflections. It's rather, okay, so this is a rather remarkable thing, and I would like to elaborate a little this point. Suppose you are given a rotation about some point Q, let's say, and through an angle, let's say phi. Now, this phi is a quantity, real quantity, modulo 2 pi, of course. Or if you wish, this is an element of the additive quotient group of R by 2 pi times integers. Okay, so if you've got a rotation like this, then actually all you have to do is, okay, so this is the point Q, and we have got, what we have got is actually a rotation about this point through angle phi, okay? So to get this rotation, all you have to do is just to take arbitrary two lines. You can choose the first one arbitrary, except of course, except of course it must go through Q, and the second one is no longer. Once you have chosen K, L is now determined. L is in fact the unique line which makes angle. Okay, here's the curiosity. Here's the curiosity. Angle, of course, phi over 2. Okay? So the rotation phi is in fact rotation about the point Q through the angle phi can in fact immediately be decomposed into two reflections in K and then in L, where K is an arbitrary. So it is rather important that we are allowed to choose one of these straight lines just as we please, okay? Arbitrary line through P through Q, and the angle between K and L is not phi, but phi over 2. Once again, this is something which I like to point out. If you've got a quantity which is modulo 2 pi, then you can't take its half. I mean, if you take, there will be two solutions to the equation 2x equals phi. Yet, if you insist working modulo 2 pi. But if you work modulo pi, then there will be a unique solution. So this is in fact a quantity modulo pi, just as it should be, because this is rotation. It's measured by a quantity, real quantity modulo 2 pi, but this is angle between two lines, so it's measured modulo pi only. Now that is a remarkable thing, and in fact, it's it can be put to use in solving many elementary problems. I have got one more interesting result, okay, which may help in certain cases. So, okay. So this is what happens to reflections. If you take one reflection after the other, well, depending on whether the lines are parallel or not, you will get, if parallel, a translation, if not parallel, a rotation. And in fact, the important thing is that you can actually take a translation and break it down into two decomposition. You can take a rotation and break it down into two reflections. Now that is rather nice. And in fact, okay, so let's ask ourselves the following question. So what are the other interesting transformations? For instance, rotation. So what happens if you take, okay, the composition of Can you say anything interesting about the composition of two rotations? Well, of course, this sort of question can be answered by using analytic geometry, so on and so forth. And yet, this breaking down into two reflections allow us to gain enormous insight into what happens. For instance, let us ask ourselves the following question. Let's suppose that I'm taking a rotation about the point P through an angle, let's say theta. And then let it be followed by yet another rotation about another point Q and angle phi, okay? Theta and phi. Of course, both theta and phi are measured modulo 2 pi. They are rotations. So what happens? So what's the result? The resultant. Now, there are trivial cases. I would like to set them aside right at the beginning. For instance, okay, so if I think it is the following. Okay, so for instance, if P and Q coincide, if P and Q are the one, happen to be the one and the same point, so if you take a rotation through angle theta about P and about the same point another rotation phi, then of course these rotations will add to give you, okay, so that's a rather trivial situation. It's these two add up to give you a rotation about P through angle theta plus phi. Okay, this is rather trivial if P is equal to Q. So this is rather trivial. So let me set that aside. That's not terribly interesting. Okay, so what happens? What happens if P and Q do not coincide? So you've got the following situation. So you've got for instance a point P, and you are looking at a rotation about angle theta through angle theta, and you've got a point, let's say Q, like this, okay, and you are taking a rotation, okay, through the angle, let's say phi, about this point, okay? Now, so about P, you rotate through angle theta. About Q, you rotate about angle phi. Put them together, what will happen? Now, to understand what happens, our strategy will be to decompose each rotation into two reflections. Şimdi bakın, interesting thing is the following. Okay, so I shall, for instance, take the rotation about P, and I shall decompose it into the product of a reflection in K and another reflection in L. What do I want? I want that the angle between K and L will be half theta. That's nice. The crucial thing is that I can actually choose one of K and L. One of them, I can choose it arbitrarily. So I will in fact choose L to be the straight line that joins P and Q. Okay? So like this. This is my L. And K is, of course, now has to be chosen like this. So K is this, okay, uniquely chosen, because this angle has to be exactly theta over 2. Okay? Now, so I in fact, so let me write down. So rotation about the point P through angle theta is now reflection in K followed by reflection in L. This L, çocuklar, I chose to be the straight line that joins P and Q. Okay? So I've been careful about separating P and Q so that I can talk about this line. Right. Now, how about L? How about the rotation about Q? It's a rotation about Q through the angle phi. So I can, in fact, take any two straight lines. Okay, let's say K and L. I can say that the rotation about the point Q through angle phi is exactly the reflection in K followed by the reflection in L, provided the angle between them is phi over 2. That's all I have to do. I can choose any two straight lines through the point Q, provided the angle between them is exactly half phi. Now that allows me a lot of liberty. So what I do is I choose the first line to be the line L, and the second line is some straight line like this. So this is this. So this is okay. So this is the point Q. Okay. So this is the straight. So I choose this to be, of course, phi over 2. So this is the straight line. Okay, so this is my K, this is my L, and this is my M, or this is my M. So now the rotation about the point Q through the angle phi is now decomposed into reflection first in L, then in M. Okay, hanımlar beyler, now we have got a very nice situation. So these two rotations, one about P and one about Q, these two rotations have been broken down into composition of 4 reflections. And just because I've been so clever about choosing the one line in each case, and I'm allowed to choose it arbitrarily, to be L, that's the line joining P and Q, I've got the following circumstance. I've got reflection K followed by reflection L and followed by reflection L, but we know that reflection repeated will give you the identity. So I can simply get rid of this part, and I find that in fact this is, so the rotation about P through angle theta, rotation about phi through angle Q gives me a rotation. Okay, so this is actually reflection K followed by reflection in M. So what is this? So reflection in K and that followed by reflection in M. So şimdi bakın çocuklar. This angle is phi over 2. This angle is theta over 2. So this angle, the angle between K and M, is obviously theta plus phi over 2. Okay? Şimdi, if this is, so there are two possibilities. If this thing happens to be pi, or multiple of pi, or an odd multiple of pi, or I'm sorry, any multiple of pi, then K and M are parallel, and so this thing reduces to a translation. I'm not telling you what translation because it's not easy to find it. If so, that's the case. P is not equal to Q, but theta and phi add up to, okay, so theta and phi, theta plus phi over 2 is a multiple of pi, means theta plus phi is some multiple of 2 pi. If that happens, this is a translation. Now, let us suppose that this is not the case. This is not the case. Then, you've got one reflection in K, one reflection in M, and these points intersect, these lines intersect in some point R, okay, since this is not, so these lines are not parallel. They intersect in R, in a point R, so that this thing, okay, so let me write it in color. So this is the interesting case. This gives you the rotation about the point R, and through angle theta plus phi, of course, if this happens. So this is the interesting case. So all the rest is uninteresting. This is the interesting case. If, okay, the angles theta and phi do not add up to some power of some multiple of 2 pi, and if the points P and Q are different, that's the interesting part, then the two reflections give you this rotation. Okay, so if P does not coincide with Q, and the sum of theta, okay, so and the sum of theta plus phi is not a multiple of 2 pi. Okay, so that is the interesting part. That's the interesting part. And okay, so that's great. So we have with this construction, not only do you find that two rotations, well, except for certain circumstances, two rotations add up. Okay, so two rotations following each other give rise to yet another rotation. Not only can you find this, of course, excluding certain banal situations, like when P and Q coincide, or when P and Q do not coincide, but theta and phi is a multiple of 2 pi. Well, if you exclude these banal situations, the concatenation of two rotations is yet another rotation. Not only do you see this, but also you can find exactly where the center of the rotation is and the angle through which the rotation is affected. So you can find them all. This is very, very intuitive, and it's very useful. I would like to present to you a problem, a very classical problem, and in fact it can be solved in many different ways, and there may be, of course, solutions which will be much more straightforward or much even easier than the solution which I shall offer you here on Blackboard. But my purpose in presenting the proof that I'm going to give you, a solution that I am giving you, is to show you, to illustrate how you can actually employ concatenation of, let's say, rotations or reflections. This kind of knowledge, how can it be brought to bear upon elementary problems? And in fact, thinking in terms of transformations has an extraordinarily enhancing effect upon your intuition. Geometry is about space intuition, about your intuition about forms, etc., etc. So it's really very important that you make nice sketches and try to intuitively grasp the thing. And if you think in terms of these Euclidean transformations, your intuitive grasp will be enhanced beyond imagination. That's really extraordinary. Okay, so I hope that this example will serve to illustrate this idea. Okay, so in fact, okay, so let's call this an application. This is in fact a very famous problem. It's a frequently asked problem, application. It's a classical problem. It's a very classical problem. Here is the thing. We take a triangle. You start with a triangle, okay, and arbitrary triangle. And then on each side, let's say ABC, on each side you construct a square on the outside, okay? Or if you wish, you take a rotation about the point C, okay, through angle 90 degrees, okay, so as to obtain, okay, so let's see, okay, so that's, okay, so let me just draw the circle, draw the square, okay, there we are. So here's your square on the line segment with one side coinciding with the line segment BC. Okay, so let me call this PQ. And let me take a square with one side coinciding with the line segment CA. And this is the difficult one. You know, when you're working on the blackboard, you tend to have an astigmatic view of the thing. So you tend to have a rather, you end up with bad pictures unless you're very, very careful. Okay, something like this perhaps. Okay, so PQ, let's say RS. So that's it, another square. The one square which has got one side coinciding with the line segment CA. And thirdly, okay, so let me do this. Okay, so this is the square that has got one. Okay, so on the outside, on the side AB. Okay, PQRSTU. Okay, so you've got these four squares, and you mark the centers of these squares. So, for instance, the center of this square with one side in line segment BC, let this be MA. Let the center of this one be MB. And let the center of this be MC. Okay, here is the problem, çocuklar. You can, of course, look at the line segment that joins A and MA, and the line segment that joins MC and MB. Okay, so the problem is, so these line segments are what we are interested in. Prove that, in fact, these two line segments are equal in length. They are equal in length. So prove that the line segment AMA, the length of the line segment AMA, is the same as MBMC, the length of MBMC. And not only that, this angle is a right angle. That the line, in fact, AMA, is in fact perpendicular to the line MBMC. Now this is okay. So that's a rather nice, beautiful problem. This is a rather nice, beautiful problem. And of course, as I say, you can solve it in many different ways. Okay, so why not be complicated? Let me tell it beforehand that perhaps many of you will find my solution somehow a little convoluted like this. Okay, so I don't know. I'm quite sure that you can find easier, simpler solutions. Anyhow, the way I like to have a look at this is is to ask the following question. Okay, so let's say, okay, so solution, let's say, is I note the following, that if I take a rotation with center, okay, MB, and through angle pi over 2. Take that. So this is the center, and I am rotating through 90 degrees. Can you imagine that? Rotating. So when you do that, the point A, so this thing is being rotated. The point A, in fact, moves into point C. You see that? A moves into C. That's very nice. Let us take also the rotation. This time through about the point MA and about pi over 2 again. So you are rotating like this through angle pi over 2. And in that case, if you look at the point C now, you will find that the point C, in fact, so this angle is 90 degrees. The point C moves, in fact, into B. So this A goes into C, C goes into B. So I find that whatever this rotation is, whatever this thing is, it sends the point A. Okay, so let me perhaps take a red. It sends the point A into the point B. Okay, into the point B. So A goes into B. Okay, so there we are. So what is this thing? What is this thing if I put them together? Our rule is that unless the centers of rotation coincide, which is not the case, and unless the angles of rotation add up to give you some multiple of 2 pi, in which case it's not true, they add up to give you pi, the result is a rotation. So this is a rotation, and I can immediately find the angle of rotation. It's pi over 2 plus pi over 2, it's pi. So this is a rotation about pi. It's 180 degrees rotation, and those rotations have a special name. They are called half turns. Okay, so I've got not. Ya hayır, beklemeyin. Okay, so tam vaktinde mi geldiniz mi? Medine'ydi değil mi? Okay, let's do that. Tamam. So I shall continue from here. Okay, so.